Hello everyone. In this particular video, we are going to solve the problem number 1.333 from Irodov, and that is related to fluid mechanics. So let us first understand the problem and then we will solve the problem step by step. So we are having two cylinders and the inner cylinder radius is given as capital R1 and outer cylinder radius is given as capital R2, and in between these two cylinders the fluid is moving, and these are the two views I have drawn which is representing the fluid flow of the fluid inside the domain of the two cylinders. Now here R1 is less than R2 and inner cylinder is stationary and outer cylinder is rotating with the angular velocity of omega 2. The fluid flow is laminar. What is the meaning of saying is that, let us say the fluid is flowing in this particular direction, then we are having the different layers of the fluid, and if the one layer of the fluid is flowing smoothly over the another layer of the fluid, then we can say the fluid flow is laminar. And in that particular case we are having the terminology that is called the inertial force and viscous force, and in that case the inertial force will be less as compared to the viscous force. In that case we can call it as the fluid flow as the laminar flow. Now the force per unit area is given as sigma, that is equal to viscosity into R into derivative of the angular velocity with respect to the radius. Okay, now in the first part of the problem it is asking to find the angular velocity of the rotating fluid as a function of radius r. For that let us take an element in between these two. As we are having the cylindrical region, for that we can take the element as a ring. Okay, let us consider this particular element. Okay, now draw it here. We are having the element like this at a particular location of, let us say, r, small r, and we can say that at these two locations, let us say we are having the torque which is acting as T1, and in the inner part of this element we are having the torque of T2 which is in the opposite direction. And if we see here, the omega of the outer cylinder is constant, that is omega 2, and the omega of the inner cylinder is also constant, that is 0, and it is having the gradient, or we can say it is varying from 0 to omega 2, but at a particular location, let us say at R, omega is not changing with time. That means it is the steady state flow. That is the definition of steady state, as the angular velocity is not changing with time at a particular location. So that means if the angular velocity is not changing with time, that means the net torque acting on this particular element, fluid element, should be 0. So we can say T1 is equal to T2 is equal to T. Okay, so both should be in the opposite directions, both the torques, and both torques should be equal in order to make the net torque on the fluid element 0. Okay, now if torque is constant, so let us find out the torque from here. So we can write the force upon area is equal to eta r d omega upon dr. Okay, now here what is this particular area? We can see here the force is acting on this particular element tangentially. If force is acting on this particular element tangentially, so we can take the area as the perimeter of this particular element into the length of the cylinder, that is L. So we can write force whole divided by 2 pi r into L, that is equal to eta r d omega upon dr. So from here we can write force is equal to 2 pi L eta r square d omega upon dr. Now here we have to find the torque of this particular force. So as we can see, this force is perpendicular to the radius. So we can directly write torque is equal to force into radius is equal to 2 pi L eta r cube into d omega upon dr. And in this particular expression we know torque is constant. Torque is constant. And we have to find the angular velocity at a particular location of r. For that, let us take r cube and dr to this particular side. We can write t divided by r cube into dr is equal to 2 pi L eta into d omega. 2 pi L into eta, that is constant, and here t is constant. Let us integrate both the sides from r is equal to capital R1 to, let us say, at the r, because at this particular position we have to find the angular velocity. And here we can write omega is equal to 0 because at the location r is equal to r1 the cylinder is having the 0 angular velocity, so the fluid near to that cylinder is also having the angular velocity of 0 to the angular velocity of omega. Now from here we can write t times r to the power minus 3 dr integration from r is equal to capital R1 to r, that is equal to 2 pi L eta, and the integration of 1 is omega from omega is equal to 0 to omega. Here we can write t times integration of r to the power minus 3 is r to the power minus 3 plus 1 whole divided by minus 3 plus 1 from r is equal to capital R1 to r, that is equal to 2 pi L eta into omega. So from here we can write t times minus 1 upon 2 r square from r is equal to capital R1 to r, that is equal to 2 pi L eta omega, and we can write t times 1 upon 2 r1 square minus 1 upon 2 r square is equal to 2 pi L eta into omega. So this is the first expression we got, where we are having the angular velocity as a function of torque, but we don't know what is the value of this torque. So for that, let us integrate this particular expression from r is equal to capital R1 to r is equal to capital R2, because at r is equal to capital R2 we know the angular velocity, that is omega 2. So we can write t times minus 1 upon 2 r square from r is equal to capital R1 to r is equal to capital R2, that is equal to 2 pi L eta omega from omega is equal to 0 to omega 2. So from here we can write t times 1 upon 2 r1 square minus 1 upon 2 r2 square is equal to 2 pi L eta omega 2, right? Now we are having two expressions where we are having t and omega here. So let us divide both the equations in order to eliminate t from here. So if we divide and take the LCM here, we will get r square minus capital R1 square whole divided by small r square into capital R1 square whole divided by r2 square minus r1 square whole divided by r1 square r2 square is equal to 2 pi L eta. From both the expression will get cancelled and we will get omega divided by omega 2. From here we can write omega is equal to this r1 square will get cancelled and we will get omega 2 times small r square minus capital R square whole divided by capital R2 square minus capital R1 square times R2 upon R whole square. Okay, so this is the expression of angular velocity we got at a particular position of r. Now, in the second part of the problem, it is asking to find the moment of the friction forces acting on a unit length of the outer cylinder. This moment of friction is basically the torque. So we have to find out, in the B part, we have to find out torque per unit length. Okay, so from this particular expression, second equation, we are having the torque times 1 upon 2r1 square 2r1 square minus 1 upon 2r2 square is equal to 2 pi eta 2 pi L eta into omega 2. So from here we can write T divided by L is equal to 2 pi eta omega 2 times 2r1 square into r2 square whole divided by r2 square minus r1 square. So we can get T upon L is equal to 4 pi eta omega 2 r1 square into r2 square whole divided by r2 square minus r1 square. So this is the expression of torque per unit length we got, and we are having the expression of angular velocity with the radius. I hope the entire procedure is clear. Thank you.